Today we're going to look at factoring cubic polynomials and using those skills to solve cubic equations. The very first issue we're going to take a look at is a couple of special product patterns. One of them is when two perfect cubes are added together. We call it the sum of two cubes. And another when we have two perfect cubes being subtracted, the difference of two cubes. And those follow a pattern that's similar with just slight differences. We'll factor them into a binomial times a trinomial, and typically that second trinomial not easily factored. Our first move, though, is to identify the a and the b. What's the cube root of each of these two terms? So let's take a look at a couple of examples. Let's look at one that might be a little bit easier to see. X to the third power. Most of us can recognize that that's x used as a factor 3 times, x times x times x. So x is the factor that's being raised to the third. How about 216? What number multiplied by itself gives us 216? Now, for my students that aren't particularly familiar with repeated multiplication, they may go to their calculators and actually try out some numbers. Try 2 to the third, 3 to the third, 4 to the third, and eventually they'll find out that 6 times 6 times 6 gives 216. So x to the third minus 216 is x to the third minus 6 to the third. So we can follow this pattern. So I'll have a minus b. My second term will be a squared plus ab plus b squared. So x is my a term, 6 is my b term. Let's put those together now. So a minus b is x minus 6. And then my second term, my trinomial term, is the a term x squared. So x squared plus a times b. 6 times x is 6x plus b squared. And this looks like something that might be factorable. There's some common numbers in there, but I would need two numbers that multiply together to make 36 that add up to 6, and those don't exist. Similarly, the sum of two perfect cubes. 8 is 2 to the third power. 125, that's 5 cubed, and we have x, so 5x to the third power. So a plus b, a squared minus ab plus b squared. Let's fill in our a and b now. 5x plus 2. 5x squared is 25x squared. Minus 5x times 2. 2 times 5 is 10x. Plus b squared, that's the 2 squared, is 4. Now let's go back and use some skills that we've already got to be able to factor some higher order polynomials, in this case, cubic polynomials. So we've got three kind of benchmarks that we're going to use. The first one is looking for a greatest common factor. Can I factor a common factor from x cubed, 5x squared, and 6x? And we see that I've got a 5 and a 6 here, relatively prime, but each one contains at least one factor of x. And I'm going to go ahead and take that x as my common factor, leaving me with x squared minus 5x plus 6. Now I recognize this as an easily factorable trinomial. Two numbers that multiply together make 6, and when I add them up, I get 5. So x minus 2, x minus 3, and importantly, I'm not going to lose my GCF. All right. Regardless of whether I can take a GCF or not, I also want to take a look and see if there's 4 factors included. Or 4 terms, I should say. If there are, pretty good chance we're going to factor this by grouping. So I'm going to take these two bunches at a time. Take the GCF from each one. X to the third, 4x squared. 3 copies of x, 2 copies of x. I can take out x squared and have a remaining factor of x plus 4. Remember, this is the distributive property backwards. X squared times x is x to the third. x squared times 4 is 4x squared. Another important piece here, if I'm doing this right, these two parentheses are going to contain the same binomial. So I'm aiming for x plus 4 here. When I start to look for a common factor here, my students will look at this and say, well, 4 goes into both, and it does. Or 12 goes into both, and it does. It turns out that 36 goes into both as well. And looking for that x plus 4 kind of gives me that target. They'll go to their calculators, do 144 divided by 4, and find out that's 36. So our two GCFs make one factor. The repeated binomial is the other. And that kind of brings us to our third benchmark, or our third key. Am I done factoring? Or as I put it in class, can I factor a factor? Take a look at x squared minus 36 and recognize that as the difference of two squares. X minus 6 times x plus 6, and don't lose that x plus 4 factor. So we talked a little bit in class this week that a cubic polynomial, third degree, is going to have 3 roots. It's going to have 3 factors. So once I get to 2, I should be on the lookout to be able to factor another one. In class, I gave students an opportunity to practice this with their table partners. If you want to stop the video now, give this one a shot and then check your work with me. Be my guest. So this practice problem is going to be factoring by grouping. 2x to the third minus 8x squared. I see a 2 and an x squared. That can be part of a GCF, leaving me with x minus 4. Now in my second term, I've got an x plus 4. I want that to be x minus 4. I have a feeling when I copied this problem that should have been a negative. Let's make it that way. So that would give me 2x squared minus 1 x minus 4. And this would be as far as I'd be able to go here. Let's take this a step farther. Now that we know that we can factor these cubics by using these various tactics, factoring out a GCF or by factoring by grouping, now I can fall back on the zero product property that we used while solving quadratics and use those to solve cubic equations. Remember, in order to use the zero product property, I need to have 0 on one side of the equal sign. I need to subtract 14x here and here. So 2x to the third minus 12x squared minus 14x equals 0. Now we look for a greatest common factor. I can take out a 2x here. (2x times x squared is 2x to the third. 2x times negative 6x, negative 12x squared. 2x times negative 7, negative 14x. My trinomial is factorable. Two numbers that multiply to make 7, subtract to make 6. Negative 7 and positive 1. So now with 3 factors, all multiplied and equaling 0, I can use the zero product property. 2x equals 0, or x minus 7 equals 0, or x plus 1 equals 0. Let's solve each of these small equations. So this graph will cross the x-axis at 3 points. It's got 3 solutions: x equals 0, x equals 7, x equals negative 1. Let's take a look at an application, a word problem. So a package, and we're given some dimensions: a height of x inches, width of 3x minus 2, and a length of 3x minus 7, and a volume of 42 cubic inches. So height, width, and length, and a given volume. We're asked to use the formula for volume of a prism to write an equation for the volume of the package, and then to solve the equation and use that solution to calculate dimensions of the package. Formula for volume of a prism. Length times width times height. So that's 3x minus 7 times 3x minus 2 times x. My volume is given as 42 cubic inches. So let's multiply these two binomials together. 9x squared minus 6x minus 21x plus 14. Combining like terms, 9x squared minus 27x plus 14. And then I've got an x that I've got to multiply in as well. All right, last thing, this needs to be equal to 0 before I can use the zero product property. So let's subtract 42 from both sides. 0 equals 9x cubed minus 27x squared plus 14x minus 42. This one we'll factor by grouping. And take out a 9x squared and left with x minus 3. Here I can take out 14, and I'm left with x minus 3. So 9x squared minus 14 equals 0, or x minus 3 equals 0. So we're going to get kind of an unusual square root here. I also have an x equals 3. Let's go ahead and plug that in. A height of 3 inches, 7 inches, and then 3x minus 7, 9 minus 7 is going to equal 2 inches. 3 times 7, 21 times 2, 42 cubic inches. So the x equals 3 gives me my values that can be used for the dimensions of the package.